Okay, in this video we'll take a look at slew rate limited behavior in an operational amplifier circuit. And to do so, we'll start with a very simple operational amplifier configuration and design it. And by design, I mean simply choose a couple of resistor values to get a desired output voltage for a given input voltage. We'll then take that design and bring it into PSpice, simulate it in an attempt to verify that it acts as we expect it to. Now we're going to find out that it doesn't, that there is some problem that we have to try to understand. And to do that, we'll calculate the required slew rate of the operational amplifier in that given circuit. We'll then uncover some options that we could take to fix the circuit so that it will operate as we expect. We'll make a change and then resimulate that modified circuit and show that it does in fact operate as we would expect. Okay, so the circuit that we're going to consider is a simple non-inverting configuration, and we're given a few things. We're told that the input voltage is a sinusoid with a frequency of 20 kilohertz and an input amplitude of a half volt. We're using a 741 op amp, and it's biased with plus and minus 15 volts. We're also given values for R1 and R4, 1 and 10K respectively. And we're asked to find R2 and R3 such that for that given input of a half a volt, 20 kilohertz sine wave, that our output voltage is a sine wave at that 20 kilohertz with an amplitude of 10 volts. Easy enough to show that the output voltage is related to the input voltage with this gain factor 1 plus R3 over R2. And so we need to figure out R3 and R2 such that the output voltage has an amplitude of 10 when the input voltage is a half a volt. So we need a voltage gain of 20 volts per volt. Now there are various R2 and R3 values that would work to give us this 20 volts per volt. I chose R2 as 1,000 and R3 as 19,000. So with those values, we should get a gain of 20 volts per volt. Okay, so the circuit in PSpice looks like this. We've got our 741 operational amplifier. It's biased with, notice here's the pin for V+. We have positive 15 volts. Here's the pin for V-. We have negative 15 volts. We were given the R1 and R4 values, and here are the selected R2 and R3 values, 1K and 19K respectively. The amplitude of the sine wave is a half a volt, and the frequency is 20 kilohertz. So with a frequency of 20 kilohertz, that translates into a period of 50 microseconds. And it's good to calculate the period because that's going to give us an indication of how long, over what time period, we need to simulate the sine wave. So here is the simulation setup. This is a simple time domain simulation. The run-to time is 500 microseconds. Now, 500 microseconds, when you have a period of 50 microseconds, that means that we should see 10 full periods of both the input and the output waveforms. I've chosen a step size, the maximum step size of 1 microsecond. So that means that for every period, we will have 50 data points. That's plenty to resolve very clearly a nice sine wave. So let's go ahead and see what our simulation results look like. Okay, so here is a plot with the x-axis in time given in microseconds, and we're going from 0 to 500 microseconds, so we should see a full 10 periods. The y-axis is voltage. Our input voltage is the nice sine wave with an amplitude of half volt. Now notice our output. It is not a nice sine wave. We would expect a nice sine wave with an amplitude of 10 volts. We're not getting that, neither the form nor the amplitude itself. It looks like a triangular wave. So we need to figure out what happened. What this seems to suggest to us is that one of the linearity constraints must have been violated. Now remember, there are 3 linearity constraints. One is output voltage saturation. We need to make sure that the output voltage does not exceed or attempt to exceed the power supply rails. Now the power supply rails were set at plus and minus 15 volts. Our desired output was only plus minus 10 volts, so output voltage saturation should not be a problem. What about output current saturation. So remember, we have to make sure that the current that the output voltage is asked to source or sink does not exceed its current saturation limit, which for a 741 op amp, a few milliamps. With the resistors that we chose and a 10 volt amplitude, we should not have a problem with current saturation. The problem that we have is with the third linearity constraint, and that has to do with how fast we are asking the output of the op amp to change with time. So again, to try to understand what happened, let's think generically about the output waveform. It's a sine wave with radian frequency omega and amplitude A. Let's take the derivative of the output voltage with respect to time. That's going to give us units of volts per second. Taking the derivative of sine wave, we have cosine A omega cosine omega t. And what we're interested in is what is the maximum value that we're asking dV out dt to be. Well, the cosine function has a maximum of 1, so that means dV out dt max is simply the amplitude times the radian frequency. Again, units of volts per second. A, in this case, we're asking for a full 10 volts, and omega is 2 pi times f. So this translates into what? 400,000 pi volts per second. That's how fast we're asking the output voltage of the op amp to change. We need to compare that to the specified slew rate of the 741. So 400,000 pi works out to be more than 1.2 million volts per second. Compare that to the nominal value of the slew rate of a 741 of 500,000 volts per second. That greatly exceeds it. So again, what we're asking the op amp to do well exceeds its nominal slew rate. We are no longer in the linear regime, and that's why we get that triangular wave. The output simply can't change faster than 500,000 volts per second. So what do we do? What can be done about this? There are a few things that we could do. One, let's say we needed that 20 kilohertz and we needed that 10 volt amplitude. What we could do is find a different operational amplifier, one that had a sufficient slew rate to deal with that large amplitude and high frequency. We're not going to do that here. Another option would be, since we've got this issue about volts per second being exceeded, what if we allowed for a lower output amplitude? A lower output amplitude would mean that we wouldn't need the output to change as fast. Again, that's another option that might be relevant for a given situation. A third possibility is, would a lower input frequency be acceptable? So the input frequency now is 20 kilohertz. What if we chose a lower frequency? Well, if that's acceptable for the given application, that's certainly an option. And that's what we're going to do in this case. We're going to go with option 3. So how much lower do we need that input frequency? Let's compare what the nominal slew rate is to what we were asking the output voltage to change with respect to time. So that's 500,000 compared to 400,000 pi. That's roughly 0.4. So if we drop the frequency to about 0.4 of the 20 kilohertz, we would be fine. Let's move even more safely. So instead of 0.4, what I'll do is just take 0.25 instead. So this certainly should work for us. So if we reduce the input frequency by a factor of 4, we're asking now to simulate the circuit at 5 kilohertz. We expect now that we will not exceed the slew rate limit of the op amp. The output voltage should be as we expect. Now, with a frequency of 5 kilohertz, that translates into a period of 0.2 milliseconds. When we do our piece-by simulation, we need to change the settings a bit to get the waveforms that we want. Okay, so, and this is what I found with simulation. So again, we're plotting as a function of time. Here is 1 millisecond, so we're seeing 5 periods of our waveform. And notice the output voltage is now a nice sine wave with a peak amplitude of 10 volts. We've achieved our goal. What is the lesson in all this? Well, in general, what we do is we start a problem, a design problem, or a simple analysis problem, assuming an ideal op amp. That's great. But after we come up with our expected output, we need to check that we are not asking the op amp to exceed any of its linearity constraints. So we need to make sure that the output voltage is not above the power supply rails, that the current being sourced and sunk from the output of the op amp does not exceed the current saturation limit of that given op amp. And then finally, we need to make sure that the output voltage is not changing with respect to time faster than the specified slew rate of the op amp that we're choosing. So again, we use ideal op amp analysis. Before we go to the lab, however, we want to make sure that we are not exceeding any of the linearity constraints. So this concludes our brief look at slew rate limited behavior of an operational amplifier circuit.